This conference will now be recorded.
Hello, everyone. We'll start here. We'll give it about 30 seconds to see a few other people are joining us. Okay, I think we'll go ahead and get started. Well, good early morning to late night. Welcome, everyone. It's good to see so many people on the conference call today, or at this webinar. My name is Steve Greb. I'm the director of GEO AquaWatch. This is part of our continuing series or webinar series that our organization offers. If you have suggestions for future webinars, please contact Mary Beth or myself, or you could even put it in the chat. Before we get started, I would just ask everyone to mute their mic. There will be time for questions at the end if you want to talk. And also, again, the chat is available if you want to put a question in the chat for Kate. Well, today we are joined by Dr. Kate Fickas, a USGS Mendenhall postdoctoral fellow at the USGS Earth Resources Observation and Science Center and the University of California, Santa Barbara Climate Hazard Center. Kate received her BS from the University of Oregon and her master's and PhD degrees from Oregon State University, characterizing wetland hydrological dynamics with landscape spectral temporal features. She has spent time as a postdoc at a number of institutions from the University of Massachusetts at Amherst, the US EPA, and she also, for 2 years, she acted as the Utah Division of Water Quality Harmful Algal Bloom Program Coordinator. Also of note, Kate is the founder and co-director of the outreach group Ladies of Landsat, and works towards increasing diversity, equity, inclusion, justice, and accessibility in the field of Earth observation. So with that, I'm going to turn it over to Kate. The title of her talk today is Calculated Risk, Leveraging Multi-Mission Compositing and Machine Learning for Managing cyanoHABs. Kate?
Great, thank you. Thank you so much, Steve, and thank you to GEO AquaWatch, all of you for having me. This is research in a study that's fresh into review. It's manuscript, so you're getting a first glance, and I'm glad to have everybody here to listen. I want to acknowledge my co-authors, Ryan O'Shea, Nima Palavan, Sarah Bartlett, and Jennifer Wolney. This has been a really fun study to work on, and I'm excited to present today. So like Steve said, I have a background in remote sensing, and I consider myself a remote sensing ecologist, but I did spend 2 years with the Utah Division of Water Quality, acting as their water quality, recreational water quality program coordinator. And what that meant was coordinating data and communication and collaboration with public health agencies and other aquatic resource managers to keep folks safe from things like harmful algal blooms and E. coli. I say this because this talk is kind of framed around making sure that we talk about these products that we come up with remote sensing and other unique and novel machine learning algorithms that we come up with, that they're actually applicable on the ground to managers who need them and want to help the public and aquatic resources. I have seen it all. I've been yelled at by the director of agriculture for Utah, the sewage lobby companies, and then also on the other side, environmental groups. So I know the balance between risk, overestimating risk and underestimating risk, and keeping a balance between making sure folks are safe, but that they still get to enjoy what little water we have in the western part of the US. So Utah sits in the southwestern part of the US. It gets very little precipitation throughout the year. Some of the valleys get a lot of runoff from the snowmelt in the Wasatch Mountains. It's famous for its snow, but that's decreasing. The state of Utah just in the last week has declared a state of emergency for drought, so things are getting dire. Most of the large bodies of water in Utah are actually man-made reservoirs for drinking water and agriculture. Those are shrinking as water warms up. Harmful algal blooms are increasing. So there's a lot going on in terms of water quality for the state of Utah that folks have to keep track of. So for today, I'll frame this around, recreational cyanoHAB management. I'll go into why I think a lot of us are on board, why we need satellite remote sensing of cyanoHABs, and then our study, which leverages a multi-mission compositing framework and machine learning for managing HABs and giving tools to managers, and then frame it back around to the implications for recreational cyanoHAB management. So the Utah Division of Water Quality, like many, if not all, U.S. states that have the resources for a recreational water quality testing program, it aims to identify and quantify cyanoHABs to protect public health in its recreational water bodies. That involves prioritizing the water bodies, collecting and summarizing data, coordinating that analysis with the different labs. And then in Utah, it's making action and advisory recommendations to the public health agencies. So the division itself doesn't actually make the recommendation. The local health departments have that final authority. And then lastly, perhaps the most important, it's communicating that risk and then the emerging science to all the stakeholders, including the public. One of my favorite pictures to show is on the upper right-hand corner there. That's a floating playground in the middle of a really popular recreational water body with a cyanoHAB, a dense cyanoHAB surrounding it. That was the day before Labor Day weekend. So generally, again, like most recreational water quality monitoring programs in the United States, there's a monitoring and testing element. I'll go into what Utah tests, and then you coordinate with your public health agencies. Sometimes it is the public health agency that ends up being the one doing the testing, all the coordinating. It's different for each state. Once advisory recommendations or public health recommendations are made or decided upon, then it's communicating with the public as to how they should stay safe in their recreational water bodies. In Utah, testing involves two types of parameters, cyanotoxins and then cell density. For the cyanotoxins, they test for microcystin, anatoxin A, and cylindrospermopsin. U.S. states rely heavily on guidance from the EPA when they frame their how they frame their water quality, their recreational water quality programs, because it's hard to have authority without authority above you. So right now, the EPA only has recommendations for that microcystin and cylindrospermopsin threshold, but anatoxin A has been found in quite a few of the water bodies in Utah, and that's a neurotoxin, can be pretty deadly. We've lost quite a few animals, including pets, to anatoxin A, so that's routinely sampled. And then despite the fact that the EPA doesn't have recommendations for cyanobacteria cell density or abundance, Utah, again, like many states, still tests for it through a variety of different laboratory elements. And that's because, it provides a quantitative measure of bloom magnitude. So that's important for a couple different reasons. Cyanotoxin expression can be ephemeral. Sometimes the sampling crew may be out there at the wrong time and the collection may not align when cyanotoxin expression is at its worst case scenario. One of the more important elements of collecting cyanobacteria cell density is that it's actually a fantastic way to communicate bloom magnitude in a quantitative way, in a science-based way, to public health agencies and the public. It's a lot more scientific and relatively quantitative to say something like there are 40,000 cells per milliliter that were collected at this specific beach, rather than there's a dense green blob along the shoreline. And a lot of states without resources to collect cyanobacteria abundance still have to rely on that language of dense green blob along the shoreline, and that can become confusing. You don't know necessarily the actual magnitude of the risk. And then lastly, cyanobacteria cells provide their own risk even in lieu of cyanotoxins. So that can be things like exposure rash from an exposure, lung irritation from inhaling the cells and ingesting them. In Utah, many of the water bodies, most of the water bodies are only tested monthly. And then in some cases, if there's resources available, once a bloom is detected of varying thresholds or magnitudes, they can be tested weekly. However, with sometimes 65 water bodies monitored across the state, that becomes a heavy burden on resources. And so oftentimes a lot of the water bodies, especially high recreation, high visit water bodies, are not monitored very frequently, which can leave the public in a great deal of risk. Once cyanobacteria is detected in a recreational water body, then begins coordination with state and local public health agencies. Again, in Utah, the Division of Water Quality doesn't actually have the authority to issue an advisory, so they make recommendations to the public health advisory by summarizing science and the different monitoring and testing and sampling elements that have been done in the specific water body. And again, this is based on kind of a holistic recommendation from the 3 different cyanotoxins and cell density. And again, cell density, even despite the fact that the EPA does not have specific thresholds, Utah and other states rely on the World Health Organization thresholds to help quantify bloom risk and magnitude. So this goes on May through October, and water bodies can come on or off different advisory levels. So that last part is communicating with the public, making sure that if there is a danger, if there is a risk, that the public knows about it and can stay safe. In Utah, there's a 3-tiered advisory approach: health watch, a warning, and a danger. On the right-hand side is a illustrative map of what Utah looks like kind of in the peak summer months in terms of how many water bodies are on a specific advisory from water quality risk. One of the big, you see in the middle there, those 3 red dots, one of the biggest headaches for the Utah Division of Water Quality and their recreational water quality health monitoring program is Utah Lake. It's a huge lake in the middle of Utah Valley, which is just to the south of Salt Lake City, but it's been plagued by harmful algal blooms for a long time, and it happens to be a highly political lake, and it's one of the biggest problems for the monitoring crew is it's absolutely massive. So 38,000 hectares, it's massive, and then it has dozens of access points. So it has traditional defined places where folks can recreate, but then you can really get into the lake anywhere you want it, especially if you're willing to wade through some Phragmites. Upwards of 200,000 visitors each year. I think that's rising, especially with COVID and folks wanting to be outside, and that includes swimming, fishing, boating, and hunting. And then on top of recreation, it's also used as an irrigation source for 20,000 hectares of agriculture. So it's a widely used lake, but it's the DWQ sampling crew is really limited in how much of the lake they can cover to make sure that they're assessing risk at a correct spatiotemporal scale. Because of its political nature, Utah Lake gets special treatment. It's sampled weekly, that's May through October during the recreation season. The crew tries to visit all the shoreline sites, but they simply can't scope the entire lake in the open water. It's absolutely massive. As the day goes on, the wind also whips through, and it can become dangerous for the crews to be out on a boat. And then, like I said earlier, the bloom moves throughout the day. Cyanobacteria are great at monitoring their own buoyancy. They can go up and down depending on environmental conditions, and then toxin location and concentration can be ephemeral. So the question is, if it's a big risk to the public with harmful algal blooms, why not just be better safe than sorry? and just place the entire lake under one giant warning or danger advisory. And again, it's highly political. There's an image problem with putting an entire lake, especially one of this size, under a warning advisory. There's a a balance that you have to strike between communicating risk and then being alarmist. At some point, the public will stop paying attention if you're constantly putting something on advisory, saying something is dangerous. I mentioned I've been yelled at by wastewater treatment lobbyists. They're the main source or one of the main sources for nutrient input and for eutrophication in this lake. They would like the image of the lake as eutrophic to be minimized. So DWQ has to balance that. And then there's economic pressures. If you put the entire water body on an advisory, you risk reducing recreation. That's how State Park makes money. It's how Utah County, which is where Provo is, it reduces the amount of visitors you get. So it's a huge balance for managers. Because of that, it's high stakes, it's huge, and with limiting sampling resources, it really lends itself well for remote sensing of water quality. And that's been done in Utah Lake since the inception of the recreational water quality monitoring program. And in a fantastic article, Stromling et al. 2020, they showed that in just one single bloom event, using remote sensing data, this is from the CYAM project, saved upwards of $370,000 in social and healthcare from reducing the risk of exposure. So the importance is there. It's a proof of concept that's been proven really well that remote sensing of cyanobacteria blooms in Utah Lake has huge benefits. In general, I won't spend too much time on this, but we know that there's a couple different proxy measurements of biomass abundance, cyanobacteria biomass abundance for remote sensing and spectroscopy. And so just in the absence of direct cyanobacteria cell density, like we are able to do in the lab, we have phycocyanin and chlorophyll A, and they can act as proxy measurements. However, as many of us know, chlorophyll A is not actually specific to cyanobacteria, and you can get mixed signals, especially if you have cyanobacteria mixed assemblages with regular eukaryotic algae in your samples. And like I said, in Utah Lake, you don't want to overestimate the risk, especially when it's the consequences of calling the lake eutrophied and identifying nutrient sources are so high stakes. So because of that, phycocyanin becomes really, because it's unique to cyanobacteria, freshwater cyanobacteria, it becomes this really fantastic way as a proxy measurement of biomass abundance. When it comes to being able to look at those two proxy measurements, we have a variety of satellite missions and sensors on board those satellite missions that we can use to try to get at it. All of the missions and sensors I've thrown up here are capable of sensing chlorophyll A, estimating chlorophyll A, but we actually only have a couple with bands specific to phycocyanin. So that's really limited the amount of phycocyanin remote sensing that's been done, although algorithms are advancing on a yearly basis. And again, the remote sensing and cyanoHAB trackers are nothing new. There's several really fantastic programs that go on that monitor cyanoHABs continuously and offer a way for managers to utilize remote sensing data in the absence of in situ data or concurrently with in situ data to augment their understanding of cyanoHABs during the recreation season. That includes CyanoTracker out of University of Georgia, GEO AquaWatch out of Canada, and then Cyan, a fantastic and widely used CONUS wall-to-wall product that's a collaboration between EPA, NOAA, NASA, and has been really a staple for a lot of the US water quality monitoring programs recently. However, none of them are using phycocyanin explicitly. A lot of them are using either an estimation of cyanobacteria abundance in relative terms, or they're using chlorophyll A. So right now we're at a point where it's time for a phycocyanin retrieval algorithm for cyanoHAB mapping that specifically, it advances phycocyanin retrievals from low cyanobacteria biomass waters, not just ones that are screaming high in cyanobacteria abundance. What's really important is that it performs well in a wide range of optically distinct aquatic regions, and then also that it's rigorously tested on wide variants of multispectral satellite reflectances. Recently, in O'Shea et al. 2021's paper, they demonstrated a machine learning algorithm of highly correlated band ratios from hyperspectral reflectances, and that showed that it was able to increase accuracy at low PC concentrations, and then it was, again, validated over a range of optically distinct regions and validated on high variants of spectral reflectances that you might see in hyperspectral satellite imagery. So we have this foundation and framework from hyperspectral industry imagery. Now it's time for multispectral PC estimation. We have a couple different options now. We have this ULCI on board Sentinel-3, which has a specific band for targeting phycocyanin, but the downside is it has that 300-meter spatial resolution, which limits the ability to capture really small lakes, and then those nearshore sites that recreational water quality managers are so often worried about, like beaches, children splashing around. However, we do also have Sentinel-2 MSI, which has that spatial resolution but does not have that specific band for targeting phycocyanin. So we can't necessarily always have it all. I think we're inching closer with more and more satellite missions every day. But what we conceived in this study was, what if we combine the two to come up with a composited framework to monitor both open water, phycocyanin estimates with Sentinel-3 ULCI, and then maybe shoreline or smaller lakes with Sentinel-2 MSI. Brings me kind of to the crux of what we're trying to get at here, and that's that we're trying to advance the quality of satellite-derived cyanobacteria biomass that can reliably assess cyanoHAB risk. And that's so that these public health managers, aquatic resource managers have a really spatio-temporally coherent picture of cyanoHAB events, throughout the season, on a given day, if you want to investigate time series across years, and then you're balancing that public health overestimation and underestimation risk with all the different stakeholder pressures that some might face. So here we develop and test a mixture density network, which is a machine learning model that I'll go over for phycocyanin from ULCI, and then we test that accuracy of the model through independent in situ matchup data, and then we apply that model to Utah Lake. And then we analyze the quality of that satellite-derived PC and the time series of that PC with in situ cell density matchups. And then really we wanted to see how our maps did against that really widely used cyan framework, which uses the cyanobacteria index, which I'll call CI-cyano from now on. Again, to see how it matches up in terms of its usability in a recreational or drinking water or public health aquatic resource management framework. And then to further characterize recreational risk assessment, we look at how our different products can help inform the spatio-temporal parameters that might go into decision making from a managerial perspective. And then lastly, on top of all of this, integrated in all this, we also use machine learning derived chlorophyll A from that Sentinel-2 imagery in conjunction with the ULCI derived PC products with the goal of augmenting that spatio-temporal risk assessment in areas like marinas and beaches, which are so often the most dangerous for cyanoHABs. For our in situ data assembly, it was really similar to what O'Shea et al. 2021 used, where we have a lot of different data across a broad geographic range. And in our data set, there was a large proportion of low phycocyanin and low phycocyanin chlorophyll A measurements. And what we're getting at here is the ability for the model to train on PC across 4 orders of magnitude, with a particular focus on low concentrations, which are typical of early bloom formation, again, compared to other algorithms that might focus on really screaming high cyanobacteria abundance data sets. Utah Lake is highly reflective across several different stations here. We have the median spectra and a 5x5 window. Again, that's not the whole lake, just specific sites that we evaluated. But here we use the Olchian MSI imagery processed to the reflectances using a specific atmospheric correction algorithm that operates pretty well for highly turbid and eutrophic waters. So the model we chose to use was a mixture density network. I'll call an MDN from now on. And these are machine learning models that combine the benefits of widely used neural networks with those of mixture density models. And through that, the model is able to learn the conditional probability density function. So that means that these models, these machine learning models, can better estimate continuous outputs of non-unique inverse problems. So for example, you might have a lot of different chlorophyll A reflectances or concentrations that equate to a similar remote sensing reflectance. So that's where having a model that is able to use the highest likelihood of the probability density as opposed to just the average likelihood might get you a much better product and outcome. We have 2 different MDNs that we use. Again, one for the MDN chlorophyll trained from MSI data, or trained on MSI data, and then one for PC retrieval trained from Olchi. For our matchup assessment, we compared the MDN PC estimates from satellite imagery to co-aligned in situ measurements from Green Bay. And then the matchup assessment there determines, the sensitivity of our model to the variance of the remote sensing reflectance resulting from atmospheric correction, and then offers a quantitative way for gauging model performance and how well it can do being trained in one area and then applied to a different one like Utah Lake. Again, why Utah Lake? Why apply to Utah Lake? So it's one of the largest natural freshwater lacustrine systems in the western U.S. It's a really unique lake. It's shallow with an average depth just under 3 meters, and again a maximum depth of just over 4 meters, which is really shallow for a lake this size. The majority of the inflow into Utah Lake comes from snowmelt and runoff. It gets very little precipitation. It's highly susceptible to eutrophication, and the majority of that is in the form of cyanobacteria blooms. Here's on the right-hand side here is the Landsat MSS image. It's the near-infrared band from September 1974. So these blooms, either cyanobacteria or eukaryotic blooms of some kind, have been captured for almost 50 years now in this lake. It's been a problem for a long time, and remote sensing has been a great way to get at water quality from space. To compare what we come up with our MDN PC maps, we wanted to use something that's widely used, which is why we chose the Cyan framework and their CI Cyano index. We grabbed all that data from their readily available data set. And Cyan does a fantastic job by providing daily cyanobacteria abundance proxy measurements for the continental US from those different satellite sensors that have that phycocyanin band, and that's at a 300-meter spatial resolution. And this is widely used by many recreational and drinking water and other aquatic resource management programs across the United States. It's a fantastic resource, and we wanted to make sure we could see how well our models did compared to that resource. And then we also wanted to make sure we were comparing to in situ data taken from Utah Lake. So because of resource limitations and kind of just the way the technology has gone, Utah Lake does not have explicit phycocyanin concentrations, but they do have a large amount of cyanobacteria cell density. So that comes in the form of knowing what species are there and then the concentration of cyanobacteria specific cells. We chose the year 2018 because we saw that there was a lake-wide continuous harmful algal bloom event that occurred really May through winter, but we chose to utilize data in the recreation season, which is roughly May through October. All of these samples were taken within a meter depth of the surface, and all were taken within 4 hours of Olchi and MSI overpass. All in all, we had about 175 data points here to compare. We also wanted to do a spatiotemporal analysis of how our model lined up. So we chose this, 9 different sites of all the different in situ sites that we had available to us based on the amount of data that each of those sites had. And then we also drew a transect between a couple of the sites to see if we could see how a bloom moved through that transect over the recreation season and how each of the different data sets compare the MDN-PC, MDN chloride, and then the CI cyano. Lastly, because this all comes down to making sure that this is a tool for risk management, we categorized all of our model data and CI cyano data into these risk management categories gathered from the World Health Organization, and that's just generally low, moderate, and high risk assessments. For model analysis, I'm not going to spend too much time going through this, but MDN-PC, you can ask questions at the end, or if you want specific details, let me know. MDN-PC from Olchi A and B had a pretty great median symmetric uncertainty of 42%, almost identical between A and B, and then a bias of negative 4.4 and negative 2.6 between the two sensors, meaning it underestimated. That's what that negative sign means. And then a really a nice slope of 0.8 for both sensors as well. So, these generally agree with the error metrics that we saw achieved with MDN-PC developed for that hyperspectral data, despite the fact that Olchi has an extreme reduction in bands compared to that hyperspectral data that this was previously trained on. And then a little bit more importantly, this also outperformed alternative PC estimation models that have been used in the past that are available for the limited number of bands. And it did an especially great job compared to alternative estimation models at low PC concentrations. It did a little bit worse when looking at the Green Bay matchup. We have an uncertainty of 135 and 85 for A and B, a bias of overestimation of 89 and 34 between A and B, and then a slope of 0.4 and 0.5 roughly. So really these metrics deteriorated relative to the performance metrics from estimates made on the Green Bay on that held out half of the in situ training data set. We think overall the reflectance limits the absolute accuracy of the model PC, but the relationship between the satellite derived and the in situ measured phycocyanin persisted over multiple orders of magnitude across a variety of sampling stations in Green Bay, Wisconsin, which is really what we're starting to get after, is that these models are able to capture multiple stages of bloom development. And then in comparison to in situ cell density from Utah Lake, MDN-PC and MDN chloride both had really good correlation to in situ cell density compared to that CI cyano from the cyano framework. And really most importantly, the MDN models represented the entire dynamic range within Utah Lake, which for recreational management is a hugely critical attribute for detection of blooms at initiation, right when they're getting started, so that managers know when the threat has begun, and then straight into the peak densities when they're at their worst. Looking at the spatiotemporal cyanoHAB dynamics, we found that the MDN-PC model was really able to capture the full dynamic range of the cyanoHAB conditions across really the whole recreation season. And here we see low PC values on the shoulder months of the recreation season. So it didn't take long, but May starts out with low PC concentrations, low cyanobacteria abundance. And again, those white dots represent days when the sampling crew and locations when the sampling crew, where the sampling crew was able to get out and sample. And then, into August and September, really high magnitude PC estimate values. We see that matching up well with the in situ cell densities of really, again, screaming high cyanobacteria abundance, really, really high magnitude harmful algal blooms that occur in the middle of summer. What this animation really illustrates is the significant enhancement of temporal resolution compared to just in situ sampling. The crew may not be able to get out there as often as they need to be as protective as they should be or would want to be, and the satellite imagery, the PC analysis here really helps augment risk assessment. And that's not to say that all three algorithms didn't respond well to changes in really high cell densities, especially that CI-cyano. All of them, these are at those 9 different stations that I showed you that we chose across the lake. All 3 captured peak cell density timings really well, but really the major difference between the 3 different algorithms, and again, that's MDN-PC, MDN-chlorate, and then CI-cyano, was in the waters with low cyanobacteria cell densities. So MDN-PC and MDN-chlorate retrievals were much less sparse in the days or near days with low in situ cell densities compared to CI-cyano, which really had a hard time capturing low cell densities. That meant that MDN-PC covered almost 5 orders of magnitude, really capturing the entire bloom life cycle from bloom inception all the way to bloom peak when things are their most dangerous. The second biggest difference here was now starting to add in that multi-mission framework, and MDN-chlorate offering the best remote observation of cell density in these nearshore regions, specifically Station 8 and Station 12 here. You can see Station 12 in particular has almost no CI-cyano data, and it has no MDN-PC data, but that MDN-chlorate is able to offer a complete time series, especially matching up with the in situ cell density, which is seen in those black stars. So because MSI has that really substantially higher spatial resolution compared to ULCHI, we're able to capture these stations through remote sensing that we may not be able to otherwise. To look at how the bloom traveled through time and space over the lake, we drew this transect. That transect's in that red line. So you can think of each line on the y-axis. The y-axis represents space. So you're moving through Station 12 on the bottom through Station 23 on the top, and then the x-axis is time. So starting in May and then going through the end of October. And what I'm showing is the three different frameworks here. So the first is just that MDN phycocyanin model. The second one is MDN phycocyanin and then composited with MDN-chlorate, filling in MDN-PC data where it's missing. And then the third is CI-cyano. And then we also have in situ data, where in situ data was taken and their values here outlined in those white squares. So what you can really see is that all 3 of these frameworks really capture, a low density bloom starting around June, and then really hitting its peak in August through September, and then dissipating down again through October towards the end of the recreation season. But really what I'd like to highlight is the stark contrast in absolute relative measurements of cyanobacteria abundance. So on that last panel on CI-cyano, you can see that it maxes out really quickly. So you're not able to get anything, any more information than either it's below threshold, meaning it's below 10,000 cells, or it's above a really, really high cyanobacteria cell density measurement. But with MDN-PC and MDN-PC chlorA, you have the ability to have absolute measurements of cyanobacteria abundance. So that means that in the early season, especially May through June, and then maybe late September through October, you have language that you can use to communicate to your public health agencies or aquatic resource managers of what bloom status is beyond we don't know if it's 0 or if it's 5,000, but 5,000 can mean that there's a bloom still hanging out, which can still pose a risk. The next thing I like to point out is that station 12, which is at the bottom of all of these panels, really shows the importance of adding MDN chlorA. So there's almost no, between panel A and B, in panel A, there's almost no data available for MDN PC because of that spatial resolution. By adding MDN chlorA from MSI, we're able to get almost a complete time series down at the bottom for that station, which sits at a little inlet between Provo Bay and Utah Lake proper. So really this composite, this middle panel, paints a really excellent picture of the cyanoHAB as it's moving across this transect through time, providing spatial and temporal coherence, giving a lot better language for managers to use in terms of communication. I'm not going to spend too much time on the confusion matrices. It really highlights the same thing I've been talking about. The MDN-PC does really well in estimating low cyanobacteria abundance, and then CI cyano has a problem in overestimating high cyanobacteria abundance. Both had that bimodality, MDN-PC low on the low end, but CI cyano on the high end. Both have different consequences for recreation management. So here we've moved towards this model that's independently tested, and then we're able to widely apply it to different lakes. And so it's even in the absence of in situ lab tested PC or chlorA from Utah Lake, we still have built a model that has been developed elsewhere and then applied in Utah Lake. So the MDNs had poor uncertainties compared to in situ, but they're still in line with the previous studies that have been using these models, and it can be attributed to a variety of reasons. And really, again, the most important thing is that these MDN products are able to represent moderate levels of PC and chlorA, not just the really high levels of cyanobacteria abundance, and they serve as this proxy to measure abundance over the entire life cycle of a bloom, especially on this region that's outside of the training data set. And again, quantifying that change in cell density from May through October on the order of 4 orders of magnitude is really important for recreational risk management. And because of that, it's also able to capture absolute values of abundance rather than above or below threshold, like CI cyano, which provides higher fidelity at bloom onset, which is, again, a change from CI cyano. This multi-mission compositing really does fantastic things for being able to have a holistic picture of where cyanobacteria risk is highest. So that on the left here is a marina that frequently has really dense cyanobacteria blooms with really high cyanotoxin concentrations. With Ulchi data, we wouldn't be able to sense in here, but by supplementing with MSI-based MDN chlorA, we can use that to, increase spatiotemporal coherence in these marinas in nearshore areas, which is hugely important. And then I want to come back to how this all fits back into a recreational water quality monitoring program. And at every stage, these model outputs can become really helpful. So right now, EPA doesn't have any recommendations for thresholds for cyanobacteria abundance, and that includes magnitude, frequency, and extent, but those are the terms that managers so often have to use when talking to public health agencies and the public. For bloom magnitude, knowing when and where areas of high risk and high magnitude cyanobacteria occur is really important. And here in our models, we showed that MDMPC really best shows the full dynamic range of the bloom. And then in places where we weren't able to sense or have estimates of the bloom because of spatial resolution issues, we had MD and Chloré that had our back and represented the blooms in nearshore. Through the Hofmahler diagram that we have here, we see that there are a lot more areas of low risk and moderate risk areas estimated through our models compared to CI-cyano. And again, predicting actual measurements of biomass compared to CI-cyano. CI-cyano is just not able to capture that same variability and precision at those levels, and instead bins them into above or below threshold. And that's significant because low risk or below threshold cyanobacteria blooms can really quickly turn into moderate or high risk blooms with the right environmental conditions. Through this Hofmahler, we also see that our models compared to CI-cyano had just with MDMPC over 2 weeks of cumulative days of PC and cyanobacteria estimates, allowing managers to potentially have immediate, accurate, and precise risk management decisions when using this data. And then when we throw in MD and Chloré, we had 30 extra days of bloom magnitude predictions compared to just PC alone, and then 48 extra days compared to CI-cyano, which is so significant when you're talking about knowing precise dates and precise locations of cyanoHABs. So MDMPC and CI-cyano may have had similar counts of total predictions, but a lot of those predictions for CI-cyano include those below threshold values, which give managers no insight into whether there's actual cyanobacteria biomass or it's a low magnitude bloom. When you remove those below detection threshold predictions, the CI-cyano biomass estimation drops by more than 50%. And then becomes 57% lower than our model predictions. So again, this is, we have spatial coverage of bloom biomass that's really critical to cyanoHAB recreational health monitoring programs. Managers need precise and accurate representation of bloom location regardless of magnitude, and they need it on a frequent, if not daily basis in order to really provide public health risks in real time. So here we have frequent satellite imagery becoming really imperative, and gaps in daily maps can lead to gaps in human health and environmental resource protection. So what's really great about our multi-mission compositing framework is that we have, MDM Chloré maps which have the ability to take cyanoHAB observations from 0 to really extensive in some of these shoreline areas, and then MDMPC to estimate open water. Again, this type of work can be utilized by managers at every step of the way. It can inform where to monitor and test for cyanobacteria biomass for targeted resource allocation. It can be used to coordinate and collaborate with state and local health agencies to communicate what the actual risk is, and then it can be used to communicate with the public so that they know and can take risk into their own hands to decide on whether or not they want to recreate in Utah Lake or any given water body. I'll wrap up there, and again, thank my co-authors, thank our our data contributors and funding sources, my Mendon Health Fellowship, the USGS Landsat Science team, the NASA PACE Science team and applications. And this was, again, a really fun project to work on, and I'm so grateful that I got to sit here today and talk to you all about this work. And thank you again. I'll take any questions.
Okay, well, thank you, Kate. It was a wonderful talk, very thorough and exhaustive study, and a great kind of example of kind of applied sciences where this research is coming together with the folks in management and trying to help understand issues and help them manage their resources. And I also like that some of this work, or you alluded to Green Bay in Wisconsin, and some of our work here in my backyard. With that, we have a few questions in the chat, and I think we'll first go to those. Mary Beth, maybe you'd like to read those, or
absolutely. So we do have three questions for you. One is a two-parter so far, and the first is from John Bratton. Was there any attempt to match model and satellite results in Utah Lake with sonde monitoring data from buoys in addition to your grab samples?
Yeah, that's a great question. We did not use Utah Lake sondes from the buoys. With personal experience and then talking with the managers of those buoys, the data managers, I know that those sondes are not necessarily calibrated consistently across years or even across the season. I think that the sonde measurements of PC and chloride are still something that are up for debate, whether or not they match up well to remote sensing reflectance data. It's something to explore into the future, especially because these in Utah Lake, those are high frequency sondes. You have every 15 minutes, so you really do have an opportunity to look at whether or not your satellite imagery matches up well with what's being seen in the lake. The sondes, again, I know from personal experience, are really can be at the mercy of things bumping into them, being cleaned. You have a lot of errant data that's not necessarily trusted, especially if you're trying to build and then test robustly in these models.
Okay, so sort of along the same line, Mona Allam has a two-part question. The first one is related to probe measurements in the field. She wonders, when measuring phycocyanin, could those probe values ever be negative?
Great question. I don't have an answer for that, but I can get you an answer. I tended to, when I was using sonde measurements, I tended to use them in a relative sense instead of an absolute measurement. Again, in Utah Lake, they were never tested against lab phycocyanin or chloride data for calibration. I think that they're working on it now. So I can't necessarily answer questions about what a negative phycocyanin measurement might be, but I always took it as a relative term. Phycocyanin proxy measurements were increasing or they were decreasing. That meant that someone should probably get out there and take a look at what's going on.
Great, thank you. Yeah, I think probably a best practice would be to change negative values to a standard limit of detection message rather than go negative. Her second part question is the 6-second atmospheric correction, can that be applied instead of acolyte for monitoring phycocyanin, and why?
That's another great question that I would leave up to maybe some of my co-authors that might be on this call. Not my area of expertise, but if you email me, I can get you an answer. I know that this specific atmospheric correction was chosen because it's shown to be robust for these types of aquatic systems. So again, if you want more, if Nima wants to speak up, or if you want more information, please do email me and I can get you in touch with those who know more.
Great, okay. I guess, Mona, you can see her email there on the screen. Please reach out. Daniel asks, have you looked at any methods to quantify the uncertainty of phycocyanin estimates?
Is that in terms of, are we checking in situ phycocyanin measurements?
Daniel, you'll have to clarify. You can unmute and speak up, or?
Hey, yeah, no, I was thinking about the estimates of phycocyanin that you're making from the satellite images. Have you looked at any ways that you would attach an uncertainty to those estimates that you're getting?
Yeah, so we did do a couple different measures of estimating uncertainty here. So that's through that Green Bay study. So we have an uncertainty measurement, of 135, and I won't go into the details of how you get that uncertainty measurement of over 100%, but it represents a range in which you're estimating over. So we have these uncertainty measurements, and they, again, were somewhat deteriorated over Green Bay when we held out half of the data. But does that get at your question, Daniel, or are you looking for a different metric?
No, that I think that answers my question. Thank you. Yeah.
Perfect, yeah.
Great. And I'm sorry, Nima, I didn't see that you had indicated you were ready to follow up to Mona's question and also Daniel's. So go ahead and speak now.
Thank you. I'll let Kate take other questions. I think we can follow up with Daniel
okay.
and Mona later on.
You meant follow up offline. Okay, I'm sorry about that. I didn't mean to give you a command performance. Okay, so you have several congratulatory notes. Amir Shagunian asks, have you taken any steps or methods to reduce adjacency effect on remote reflectance values?
Another great question for Nima. That's not my area of expertise in this, but I know that they're taking steps towards making sure that adjacency measurements are not interfering, but that's as far as I'll go, and again, I'll let Nima follow up.
Yeah, I can quickly address that. Thanks, Amir, for the good question. Utah Lake is quite large, and we don't see adjacency effect being a major problem, especially in and around the center of the lake. In the marinas, nearshore environments, definitely adjacent effects should be taken care of. And it's an R&D area, and we're looking into it, not just us, but the entire community. And we're hoping to be able to have an answer for nearshore pixels hopefully soon. Thank you.
Okay, so there is one more question, Steve, in the chat. I don't know if you want to take that or you just want to go to the audience. Anybody who wants to ask verbally.
Yeah, if there's people that have been patiently waiting, that we're almost to the top of the hour, but we don't have a raise your hand, but if you care to unmute yourself and ask a quick question. Don't be shy.
Okay, we can pivot to Shelley's question in the chat. Shelley Tomlinson asks, she apologizes, she may have missed something, but how are you filling in the Olchi data with the Sentinel-2? You mentioned getting additional 40+ days, but with the lower temporal resolution of Sentinel-2, she's confused about how you got that much temporal improvement. Spatial improvements made sense to her though.
Yeah, so great point, Shelley. That's a spatiotemporal improvement. So I'll draw you, this is specifically to the Havmaler. That's on a specific site that only can be accessed, or mainly can be accessed by MSI Sentinel-2 data. We have those extra days of detection, not necessarily across the entire transect. That's where those extra days are coming from.
Okay. I did have a few questions, although actually most of them have been addressed, but just one quick question, since you have this slide up here on the screen, is, on the MDN PC chlorophyll middle slide, looks like there's some growth like late, I don't know, is it late November or December, which kind of surprised me. Can you comment on that, or do you actually see these high concentrations late in the season?
Yeah, I can't say for certain what these were, especially because we don't have a lot of in situ data especially in that late part of October. What I can say is that Utah Lake has had harmful algal blooms go into December. Those are becoming more common with lower ice cover and reduced ice cover and later ice cover because of climate change. So it's really likely that Chloré picked something up potentially that PC and the other ones didn't. We also see it confirmed with the CI cyano that maybe there was something going on there. They have that's detecting a high threshold at like the very last day of October too. Yeah, so Utah Lake has a really interesting phenology where it typically has like an aphanizomenon bloom early on in the season, then it crashes in September, and then you get this growth of microcystis, spermopsis that can go through the fall season until it crashes or until ice cover comes. But Utah Lake has seen harmful algal blooms even under ice cover through the winter.
Okay, thanks, appreciate it. Well, it's the top of the hour, so maybe we should bring this webinar to a close. We had a wonderful turnout. There's a lot of interest in this work, Kate, and we, again, really appreciate you taking the time to put this presentation together and share it with the AquaWatch community. Again, for everyone else, if you have thoughts or are interested in giving a webinar, please contact us, and we'd like to hear from you or hear about your work. So with that, enjoy the rest of your day, and thanks again, Kate. Appreciate it.
Yeah, thank you, Steve. Thank you for having me.
You bet. Take care.
Have a great day, Kate. Thank you.